All right. So now I'd like to introduce our next speaker, Inmar Givoni. Inmar will be taking us through the journey of AI and ML applications over the past decade. I hope you all enjoy.
Hello. Is everything good for me to go? I'll take that as a yes. All right, cool. So, hey everyone. I was invited to give this talk by the organizing team, and they told me that the topic, the theme is AI for good. And honestly, I wasn't sure that that's something that I had a lot of things to talk about. So instead, we decided that I'll kind of take you through my personal journey of how I applied AI in my career in the last decade. And whether it was for good or not, I'll kind of let you be the judge of that. So in 2011, I started working on real-world applications of AI. And today, I'll tell you, hopefully, some fun things about that. But in order to get you there, I need to tell you a little bit more about who am I and how did I get to a point where I started working on these applications. Spoiler alert, the end of the journey is that I'm actually no longer in AI. This is fresh news from 2021. I do care a lot about people, young people starting out, which is why I've agreed to give this talk. I am trying to wind down my public speaking, so I figure this is possibly one of my last such opportunities, and I can say whatever I want and not worry too much about the consequences. Also, I can't see any of you, which as a public speaker kind of sucks. So I need to somehow entertain myself. So I don't know, this talk might get slightly outrageous. I promise to talk about porn and farting in the context of AI, or maybe not. But before we even get into that, I also really need to tell you what AI is. And it's a bit of a pet peeve of mine because people use terms like machine learning, deep learning, and AI completely interchangeably. And they're actually not interchangeable. Now, to be perfectly honest, I've gotten over it. I've gotten on with the program. This is how people talk about it, but it's not all the same. And maybe if you take one thing, if you learn one thing from this particular talk, this will be the thing. Okay, so let's start with that. As soon as it works, no one calls it AI anymore. This was an observation made by John McCarthy, who was one of the fathers of AI. He was a brilliant computer scientist who, among other things, developed the Lisp language, garbage collection, and a bunch of other important things, and coined the term AI. And he already noted that the goalpost of what is AI keeps moving, partly because we don't really have a good definition for intelligence to begin with. But the definition that I like to go with is that AI is a branch of computer science that's concerned with the automation of intelligent behavior. And the goal of AI research is to create, the research area is to create software that imitates intelligent behavior. Now, the important thing about this definition is that it told you nothing about how to go about it. It's not prescriptive. You can do it by building an expert system where you basically list down a whole bunch of rules, and that will be, an AI. You can search through all of the possible solutions and somehow score them and pick the best one. So you can brute force your way. You can represent knowledge and relationships. So there is no prescribed method of how to go about solving it. It's a problem statement that's very general. Okay, now, what is machine learning? Machine learning is the study and development of computational approaches to automatically making sense of data. So this is why the word learning is there. It is prescriptive. It tells you you're going to go about generating intelligence via using examples and using data. And this is very similar to the way children learn from examples. And so machine learning algorithms learn from data, they learn from examples. So it's a very different notion of general AI because it tells you, there is something that's got to be there, which is the use of data. And it is a branch of AI because this is one way of arriving at intelligent behavior by learning, by observations. And systems, these are systems where the knowledge is acquired through experience, improving over time as you get more data. And so a very canonical example is that of supervised learning, which is a particular way of a particular type of problems within machine learning. In supervised learning, the data that we get is labeled. So The canonical example, can I differentiate between photos of dogs and cats? The way I do it is I give the algorithm a lot of photos of dogs and cats, and it does something. We're not going to talk about that. And then the next time it sees something that it hasn't seen before, it should hopefully, with great accuracy, be able to tell us if it's a dog or a cat. The point being that I didn't actually tell it anything about what a dog or a cat looks like. I didn't say, look for some whiskers and so on and so forth. It just learned it automatically from the data. So we're not trying to describe, in code and if else and so on. We're just learning it through the machinery of the machine learning framework. And so we can say that machine learning is a sub area within AI. And then deep learning. So deep learning is a particular family of solutions or algorithms or techniques that are motivated by the brain and the cortex. So they're not really modeled after the brain, because the brain is far more complicated and we don't actually understand how the brain works. But we do know that there are, for example, neurons, and neurons get a lot of inputs, and then they do some sort of a computation on the input and they provide an output. Another thing that we know about the brain, or the cortex in particular, is that it has this notion of layers. So you have neurons that are all taking the same type of inputs and doing their computations, and then they send their output to the next layer and so on, and the next layer. And so neural networks have been around for a long, long, long time, and the simple ones, the ones that don't have a lot of layers, the shallow networks, we were able to train them to solve very simple tasks, and that was nice. But it was very clear for deep mathematical reasons that neural networks that have a lot of layers are going to be have the capacity to solve very complicated machine learning type formulations. The problem was that for many, many years, no one was able to train the damn thing. So by training, I mean, taking a whole bunch of data, pushing it through the machinery and getting a network that actually does something that is sensible with high accuracy. And more recently, in the last decade, we finally were able to solve, to crack this problem of how do you train deep neural networks. And as a result, there was also some, maybe not deliberately, but there was a rebranding of artificial neural networks with the name deep learning. And the cool thing about deep learning is that it gets in many, many different tasks state-of-the-art results. So object recognition, natural language processing, speech recognition, and so on. Most of what you see out there and use every day pretty much is based on deep neural networks or deep learning. And so now we can say that deep learning is a subset of solutions within machine learning, which is a particular approach for learning from data, which is within AI, which is the general search for how to generate artificial intelligence. Okay, and so now that my pet peeve is over, we can get back to my story. And what did I do before I actually started working in industry on real-world applications of AI? So after high school, I actually went to the army because I'm originally from Israel and we have to go to the army. And so I went into the intelligence. So I guess I was halfway there. It was not yet artificial, but it was the intelligence. Back then, I was not allowed to tell anyone what I was doing or what unit I was part of. But, just like everything in the world, things have changed. Privacy is not that much of a concern anymore, apparently. So the unit I was in, which was called 8200, it's now famous enough that it has its own wiki page. I actually just checked and it's got a LinkedIn page. For all I know, it's going to get its own TikTok account. And this is basically where I learned how to write and architect software. We weren't really doing AI, and definitely we weren't calling anything that we were doing AI, but thinking back about some of the stuff we did, we were trying to tackle very complicated problems, and definitely, even though it wasn't machine learning, you can definitely say that some of the work we were doing was actually AI. After finishing my stint at the army, I wanted to go to university. I went to the Hebrew University in Jerusalem. And what I really wanted to do actually was to be a neuroscientist. I wasn't thinking of machine learning or anything like that. I didn't actually know that there was a thing called machine learning. I was thinking to myself, what should I study in order to be a neuroscientist? And the reason I wanted to be a neuroscientist is because I thought the brain is the most interesting problem in the world. Like, we're all carrying this thing around with us, and it does a lot of things, and we really don't understand it. It's kind of mind-blowing to the extent to which we don't understand how it works, especially compared to other organs in the body, where we have a fairly good mechanical, biological, and so on, chemical understanding of what this thing is and how does it work. And so there was no undergraduate program in neuroscience, and I thought, what would I study that will best prepare me for a graduate degree in neuroscience? And I decided on computer science and biology. Computer science because I wanted to get more formal education of the theory of computer science, and biology because I, up until that point, have managed to not study any biology deliberately. I didn't like it, and I thought, okay, but if I want to be in neuroscience, I should probably learn some biology. It seemed like a good idea at the time. Particularly, it was a good idea given the fact that I didn't ask anyone whether it was a good idea or not. That might have been a bad idea, but anyways, it's too late. So that's what I studied. The Hebrew University in Jerusalem has a very nice campus. It has the archive of Albert Einstein. So if you're skipping class, you can go and admire his incredibly neat handwriting in one of the libraries. It also has all sorts of sculptures and public art along the campus. This one is my favorite. It's called A Draped Seated Woman. It's by an artist called Henry Moore. And when I moved to Canada, I was happy to discover that the AGO has a copy of this one, which delighted me. I actually called it The Farting Woman because it almost seemed like she was kind of, gently lifting her bum so that she could let one loose discreetly. And between visiting the lady and visiting the library, as well as visiting the computers room, which was this underground dungeon where we spent almost all of our time writing software assignments because almost no one had a computer back then, let alone a laptop. I took a course, and the course was called Introduction to Machine Learning. I had no idea what it was going to be about, and it absolutely blew my mind. So what I liked about it, and what unfortunately I think might be slightly missing from what's happening right now, because deep learning is so powerful, but it uses so little mathematics in a way, is that machine learning in general uses a lot of pretty deep mathematics, calculus, linear algebra, optimization theory, probability and statistics. And so all of these things that I was studying in my other classes that were perhaps not really connecting, really clicked, and were all used in these beautiful ways in the study of machine learning, as well as, of course, software engineering. And it was, at the end of the day, a way to do, to write code, to write algorithms in a way that I've never thought about before. And as I was studying all of that and getting excited about it, I also thought about how it's the mirror of neuroscience in a way, because instead of trying to understand the brain, we're building machines that try to mimic the brain. And so I decided that rather than go and do a graduate degree in neuroscience, I will pursue a graduate degree in machine learning. And so I came to Toronto to do a PhD in machine learning. Toronto, University of Toronto being one of the best places in the world today, but also it's been like that for many, many years with a very strong team of faculty and graduate students doing machine learning. So I came to Toronto, which is also a beautiful campus. No farting lady, but a lot of libraries. It's got the largest library system in the world, from what I know. I did a direct PhD, so that's without a master, and that still took me about 6 years. So I had plenty of time to visit all of these different libraries. Probably the most famous one is the Roberts Library, which is, I don't know if you knew it, but it's inspired by a peacock or a turkey. The battle still rages on Reddit. It's certainly visible from this angle if you've never noticed it. And if you don't remember anything about the AI, ML, DL distinction, maybe that's the one tidbit you can take from this talk, that this is a peacock. But anyways, while I was doing my PhD, I did a few internships. This is something that I highly recommend all of you try to do. I did it only in my graduate studies, but if you can swing it during your undergrad, that's great. So a professional engineering year or a summer internship, because it gives you a really good sense of what's out there and what does it mean to apply what you're studying in the real world. And in one of my internships, I went to Cambridge, England, and I joined the Microsoft research team that was working on machine learning algorithms for Kinect. So Kinect, the gaming system, it has a bunch of sensors. It needs to help you play games in a way that's more fun. And one of the first things that you need to solve is, given the sensor reading estimate the pose of the person, meaning where are the different limbs of that person standing in front of the Kinect. So this is actually one of the first examples of real-world applied machine learning that I did that was related to real people, real consumers, real applications. But that was just an internship. Back in school, I was still doing very abstract research. So then I graduated, and now we can kind of get down to business. So a decade of AI, which of course is machine learning and deep learning, really, of stuff that I've been doing in my career. So the first place I went to, excuse me, is a company called Altera, and that everything that I'm going to talk about is here in Toronto. I stayed in Toronto after my PhD because I really like the city and Canada in general. So there was a company called Altera, now they're part of Intel, and they were building something called an FPGA. Now, how do you know if someone is computer science or electrical computer engineering? This is not a joke, this is actually a true statement. You ask them if they know what an FPGA is. If they are electrical computer engineering, they probably do. If they're computer science, they probably don't. So for the computer scientists in the room, an FPGA, a field programmable gate array, is a piece of hardware. It's a chip that is programmable, meaning that you can, deploy instructions into it, not every second, but on occasion. And so this is kind of a nice middle ground between writing software, like executing software on a CPU or even a GPU, which is relatively slow, relatively speaking, and executing it on a piece of hardware that was specifically designed only for one thing and can never do anything else. So that's the fastest, but it takes a lot of time to develop this type of hardware, and it's very bespoke for a particular problem. So FPGAs are kind of in the middle. Now, back then, I wasn't actually doing machine learning because no one was using FPGAs for machine learning in 2011. So I did that for a year. I learned a lot about hardware, a lot about algorithms for related to hardware. It was a lot of fun, but I really missed doing machine learning. The reason that I'm telling you about it is just as a note how things have changed in this last decade, because there is a lot of development, of course, in AI, and it's not just at the level of the models and the problems that we're able to solve by, writing a new type of architecture or network. It's also across, more development of general use libraries that people that are practitioners, non-experts can use, frameworks, infrastructures, deployment tools, a lot of things that go along with the core models, as well as hardware. So there is a lot of interest in the hardware community about how do you build computer chips that are specifically designed to rapidly be able to run these types of neural networks or use low power consumption and so on. So it's a huge deal. There's a lot of companies doing it, including companies that are focusing on FPGAs and trying to figure out, and have figured out in many cases, how do you use them to rapidly to basically optimize, accelerate neural networks. Okay, so then next I went to work in a place called Kobo. Now, if I could see you, I would ask you how many of you know what a Kobo is, but I can't. So it's a Canadian Kindle. That's one way of saying what it is. Actually, it was started by a bunch of Canadians, and the headquarters of Kobo are here in Toronto. But it was acquired by a Japanese company called Rakuten a few years ago. So technically, it belongs to them. And I went to work there as a research scientist. Now, back then, a lot of people were asking me, like, why do you need machine learning at Kobo? How do you use it? And the answer is you use it in many, many, many different ways. So let's think about it. So first, it's an app and a website that allows you to buy books. So it's an e-commerce platform, meaning that your things like search and recommendation can be optimized using machine learning. So, when you search, the order of the results, recommendation systems are basically a form of machine learning. It's also an app and device for reading books. So you can collect a lot of data from how people actually engage with the books that they buy and how they read it. And you can make use of it in all sorts of interesting ways. So I got a chance to do a lot of different interesting projects as an individual contributor, as a research scientist, kind of building and writing and deploying my own models. And I'll give you a few examples. So the first one is about a personalized experience when you go to the store webpage. So, there are different types of sales going on, different types of highlight around different books of the month and so on. So, they're laid out in these various widgets or blocks of content. But of course, you know a lot about users and what they prefer, and why bother showing them things that you don't think are going to be interesting for them. So personalizing the experience of the website for each user can be cast as a form of a very simple reinforcement learning setup. And so that's one of the models that I worked on and we deployed. Another example is plagiarism. So like many other sort of similar platforms, Kobo allowed anyone to say, hey, I just wrote a book. I'm an author. I can self-publish on the website, so I can just upload a piece of writing, decide how much I want to charge for it, and there you go. I'm published author. Now, when you do that, there are some rules about what you're allowed to upload and what you aren't. And one of the things you're not allowed to upload is someone else's book, right? But of course, people will be people, and they do this type of stuff. And so you need to be able to compare every book to every other book in your catalog. Now, of course, you can't just do a brute force comparison of word by word, because actually that's not going to work. People are smarter than that. They'll tweak things around such that like a full-on comparison will fail. So what you really need to extract is some form of a fingerprint of a book, and then be able to do these types of comparisons. So that's one of the projects I worked on. And then another one that I'll tell you about in a bit more length is, and also because I promised, is something that was quite unexpected to me at the time, which is I was asked to build a porn classifier. So again, people were allowed to write any book they wanted and upload it to the website and sell it, except that the company did have some level of discretion around topics that they said, okay, you know what? We don't want books that are on this particular topic on this website. And these are things that are kind of taboo. So to give you an example, things like, bestiality. So didn't want any of that on the website. So we needed to be able to basically automate the process of determining what kind of content was in a book. There are other use cases for why you want to know if a book is pornographic or not. For example, within the bigger store, there was a kids store embedded. So you never want to show up that content in the kids store by some sort of an automated method. You send people emails. All of these things are generated in an automated fashion. Maybe you want to filter out any recommendations for porn-based stuff, just because emails are a little bit more sensitive. If you're typing something, you're searching for something, you have an autocomplete feature, but maybe you want to shut down autocompletion on pornographic titles because some of the titles are really unpleasant, and maybe someone who's looking for something else is not interested in seeing that kind of stuff. So at the expense of maybe being less useful for the one who's actually looking for that title, we might not want to show it to other users. So actually, even though here on the screen I have it as porn versus not porn, it was actually these different levels of how pornographic something is, from like nothing at all to violating the policy and a couple of levels in between. And that was perhaps my first ethical challenge for myself, because I personally did not like having to deal with this content. And I was thinking to myself, is there anything really problematic about it, right? And I went through my own kind of ethics session in my head, and I determined at the end of the day that even though some of the things that were described in these books and even titles were actually illegal, at the end of the day, this is just coming out of someone's imagination, as opposed to, say, someone going and creating a film, maybe a snuff film of that content, which is someone was hurt probably in that process. So, no one was hurt by the fact that someone sat down and wrote something, and if someone chooses to read it. And so I decided, okay, I can do it. At the end of this project, after I figured the model and, tested it and ran it and we deployed it, I gave a presentation about it to the whole company, including our new Japanese CEO. And this was one of these times where I thought, I'm going to do something and I might get fired, which is, at some point in your career, you might want to give it a try. as long as you're not doing something illegal. And the talk was about an introduction to machine learning. I actually wanted to take people through the process of understanding a little bit about what machine learning is, and I used, because I like using pictures of cute animals, and you're probably thinking, oh, there she goes about the cats and dogs again. But no, I was explaining the porn classifier and how it worked. So this was a presentation where I got to stand on stage and say things like "dirty little bitch" and "a shaved pussy," because that's what that is what in these pictures, and that is what I had to deal with. And it was probably the most outrageous talk I've ever given, and somehow I did end up keeping my job, so that was good. Oh, interesting. There should be. Oh, okay. So I'm hoping that you can see. Let me just double check that you can see the video. Yeah. Right. So the next place I want to work in is Kindred. Kindred was a small robotics startup. I really wanted to know what it's like to work at a startup, and I also really like robots, so it was super exciting to be able to work on them. At that point, by the way, I was no longer an individual contributor. I was no longer writing the code myself. I was heading teams, so that started at Kobo, and when I joined Kindred, I came there to lead both the software engineering and the machine learning groups. And the application there, as you can see, is warehouse automation. So, the way that warehouses work and how they fulfill your orders when you place an order, it's got this workflow and logic of its own, which I'm not going to go into explanation, but at some point you do have to take a whole bunch of stuff and sort it into individual orders. So this is what you're seeing this robot basically doing. There is like a bin, and a whole bunch of things get thrown into the bin, and then now the robot has to pick them one by one, determine what order they belong to, and sort them out. And so what kind of things do we need machine learning for here? So first of all, the detection of these different items. That's like computer vision, pretty standard application. Grasping, how do you learn how to properly go and use this robotic arm and grasper to lift something. Also, motion planning. How do you design the motion path of this arm? This can be cast as a less common, but this can also be cast as a machine learning problem. Error detection. Maybe you pick not one item but 0 items. Maybe you picked not one item but 2 items. So how can you determine through a machine learning application whether you've done that? And actually, we had a very cool setup for collecting training data, where basically we put a very simple kind of grasping algorithm, and we had in the lab here in Toronto, we had a whole bunch of these robotic arms, and they would just kind of willy-nilly try to collect stuff, and then take a picture of whether there is something in the gripper or not that a human would actually label later, and that way we could go home, and the next morning there'd be a few new 1,000 examples of grasp attempts, and after quickly labeling them, we would have some new label data. And of course, you can also try to automate the labeling as well. So that was a little bit about Kindred. And then the last place that I was in is Uber ATG. And so we were working on self-driving. And of course, there are many, many applications of machine learning and deep learning to self-driving. I cannot even begin to cover them all, but I want to give you a bit of a taste for that. And so one of the big problems that you need to solve in self-driving is called autonomy. And autonomy is basically the idea of how do I get from sensors to controls. And what I mean by that is the car has all these sensors, cameras, radar, sonar, ultrasonics, LiDAR, which is this laser-based technology. It's a sensor that tells you how far things are. And really, you need to take all of this information and translate it into steering, so right and left, and acceleration, deceleration. This is the problem of driving, right? Now, traditionally, people have divided it into sub-problems. So perception, prediction, and motion planner. So in perception, basically the question is, where is everyone that's interested in what I'm seeing around me right now? And by everyone here, or more technically, we call it actors, I mean pedestrians, cyclists, motorcyclists, cars, trucks, and so on. Given that I've solved the perception task, there is the prediction task. So where is everyone going? Where are they going to be in the next half second, 2 seconds, and so on? Once I solve that, I can talk about how do I plan my own trajectory. So I need to get from this lane, let's say, to the other lane. So I need to do it such that I don't hit any of these actors. So this is why I need to know where they are and where they're going, such that I don't violate any rules of traffic, and such that the driving experience itself is pleasant. Because even though maybe mathematically I can maneuver safely by slamming on the gas, slamming on the brake, and doing like a crazy twist, it's not going to be pleasant for the riders. So we also need to take this into account. And now that I've planned my trajectory, I can just send that to the control, the acceleration, deceleration, and so on. And that's basically the way that people have been thinking about it. So each one of these subtasks is in itself can be cast as a machine learning problem, or you can take the approach of saying, let's build one monolithic neural network that is basically the end-to-end solution, so going directly from sensors to controls. There are pros and cons to each one of these approaches. The big problem with using an end-to-end network is basically interpretability, explainability. If it does something silly, you really have no idea why it did it. So a lot of the work done at the office was trying to march towards this vision of taking the best of both worlds, so having an end-to-end system that is both interpretable and explainable. Now, the things that my team was working on, we weren't working on the core modeling and the core research. That was done by a group of researchers who were dedicating their time to that. But there is another big problem in the world of AI, which is how do you take these prototype models that work very well on paper or on someone's computer or even on the cloud, but they're still prototypes. How do you make them into production systems that actually work in the wild reliably and so on? And just to give you a taste of one of the challenges in that, and there are many, many different challenges. It's actually a big area of machine learning engineering, is the problem of runtime. So for example, maybe someone developed a really amazing perception algorithm. Its accuracy is 99.999, but it runs in 200 milliseconds. Well, that's just not going to cut it, because we don't have 200 milliseconds when we have to run it on the car. Maybe the budget is 70 milliseconds. So then how do you take an algorithm that runs in 200 milliseconds and turn it into an algorithm that runs in 70 milliseconds, and it's a neural network? Well, in order to do that, you need to know a lot about hardware. Let's say that we're running it on a GPU, so its architecture and how to optimize for it. You need to know a lot about software engineering, how to write it in a way that's fast and efficient. And you need to know a lot about neural networks, how they work, and what are the different knobs and parameters that you can change so that you don't lose the accuracy, or you lose very little accuracy and you gain in terms of runtime or other consideration like power consumption. And so these are some of the problems that people on my team were dealing with on a regular basis. That's pretty much, I think, all the time that I have before we take some questions. I gave you some examples of how machine learning and deep learning and AI, which are not the same, are applied to real-world problems. I'll let you make your own determination whether it's good or not, and I promise that I'll tell you what I'm doing next. So I'm taking a break from AI, not because I don't like it, but because I've become very fascinated with something else, which is writing fiction. So a shameless plug, if you're interested in reading some of the stuff I write, this is my website. You can go there and read some short stories. Thank you for listening, and I'm now happy to take questions.
Thanks so much, Inmar. It was super inspiring hearing about your journey, and also your unique perspective and teachings on AI are like super refreshing. Our delegates also loved your slides, so thanks for that. So I'll dive into the questions now. Okay, so this is a good one. So what role do you believe multidisciplinary engagement can play in consolidating various ideas revolving around artificial intelligence?
I don't know that I understand the question. Maybe we can clarify what multidisciplinary engagement means.
I think just people from different fields kind of coming together.
Yeah, so I think like that's not unique for AI. I think in any domain having, I'm a big believer in diversity in general, and I think as we have different people with different approaches, different ideas around the table, different backgrounds, and that can be educational, and that can be ethnicity or other types of perspective, the better the solutions we can come to. This is not just my own kind of intuitive, anecdotal perspective. There's been studies that show that, and so I think it's very exciting to see, like, even when you go back to more classical machine learning research, you see a lot of inspiration from different fields and a lot of it is because someone like, a physicist or, someone from operational research or other fields come into it and take a look. And even, like back when it wasn't as popular, there wasn't a lot of research done on the ethics of AI or all of these things. And when you showed it to the general public, they started asking these questions because they were interested in it. And that in turn made the researchers try to come up with mathematical formulations and approaches to how do you actually quantify things like privacy, how do you ensure privacy from a heavy mathematical perspective. So even the engagement with people who are non-experts drives forward an interest in particular developments in a field. So I think it plays a great role.
Great, thank you for that. So just kind of back to more the beginning of your presentation, because of course these questions came in as you were speaking.
Yeah.
So were there any worthwhile parallels between biology and machine learning that helped you with your career?
That's an interesting question. I mean, like, I think you're asking beyond the obvious one of neural network, but I think I don't have anything that like jumps into my mind right now. But again, I think it does go back to knowing about a completely different other way of thinking, and whether you know it or not, you're bringing some of that understanding and knowledge into the picture when you're trying to solve a problem. Like you have that knowledge embedded somewhere, and it might come up. And maybe if I had a little bit more time, I would have, I would be able to think about something that, I mean, definitely in coding, right? Like if you think about the central dogma of biology, DNA coding to RNA coding to protein, there is this notion already there of a code and redundancy of code, and these things are somewhat related to cryptography. So there's always, when I think of compression, right? So our brain does compression, obviously, in one way or the other, and compression is really important in computer science. So there's like always these little parallels that because you know some area, they'll come to mind when you're thinking about a solution for another one.
Yeah, that was a great response, and the mRNA relation is really interesting there. Okay, so I think we just have time for one more. So this is more based on your degree and your process in school. So how do you feel about completing a Master's of Science or PhD in engineering? You mentioned you just jumped straight to the PhD. So do you recommend that to students and aiming to enter the field of AI ML?
So I think it's really hard to know. So the person you are when you start your graduate journey and the person you are at the end, they're not going to be quite the same person. You learn a lot along the way, and you understand yourself better and better, and you understand what is really interesting for you versus what other people think that you should be doing. You understand how to prioritize hopefully how to prioritize what you like versus what other people think you ought to be focusing on. And so I don't really have a good answer to that. I think that the only thing that I at least to me, going to do a PhD because you want to earn more money at the end, for example, that never seemed like a good, reason to do it, and mostly because it requires a lot of perseverance. Like it's almost never easy for anyone to do a PhD. It's very rare to find someone who just like breezed through the whole thing, and most people end up, myself included, going through like times where it seems like it's never going to end, and you always, like everyone I know about, wanted to quit at one point or another. So you really need to to have some sort of deep interest in what it is that you're doing right now, not just in what you might be able to do or what it might be able to accomplish once this is done. So so you gotta have at least some sense of this is what's exciting for me to be thinking and spending all my time on right away. And as for the master's versus PhD, again, you kind of going into doing research, my sense was that I really didn't understand what it meant. I spent a lot of time talking to people doing research because I was like, so what is research? What is this thing that you're talking about? I know what it is to take a course and take an exam. I know what it is to do a project, but what do you mean when you say research? And I had a whole bunch of people tell me what they did, but that really didn't mean much to me. And it was only when I started doing it, it's like what people call experiential. When you go through it, you're like, oh, okay, now I get it. So so it's also hard to know whether to allocate a small amount of time to this or like a full. I didn't intend to do a full PhD. I started in a master's program, and I just halfway through kind of got convinced to reclassify. So so it is easier to start with a master's and then make your decision, definitely, if you don't know.
Yeah, thanks so much for that advice. That's it's very true. Okay, so thanks so much again, Inmar. And we're going to take a brief break. And at 10:45, the design team showcase will begin, and then it'll run till 12:10. So if you please can exit the main stage, and on your Hopin navigation page, select the Xbox